Ok. Bueno, pues bienvenidos a todos. Bueno, ya estabas transmitiendo, ¿verdad, Andrés?
Sí, ya estamos al aire.
Bueno, bienvenidos a todos a nuestro segundo día de Átrica, un encuentro internacional de diseño computacional, fabricación digital y tecnología aplicada a la arquitectura. Yo soy Adriana Cerón, soy miembro línea de la Liga de Estudiantes de Arquitectura y pues bueno, somos una organización de estudiantes sin fines de lucro con la finalidad de aprender más allá de lo que la escuela nos enseña y con el objetivo de ser mejores profesionistas. Y pues bueno, Átrica es un evento muy especial para nosotros, puesto que es nuestro primer evento internacional con la participación de ponentes de 4 continentes del mundo que vienen a compartirnos su conocimiento por medio de charlas, de talleres y de foros. Y hoy es el turno de un ponente muy importante para nosotros que nos transmite desde Australia y es el Dr. Roland Snooks. So welcome, Dr. Roland, to our event Átrica. Thank you for accepting our invitation and for coming. It's a really honor to have you here.
It's a pleasure to be here. Thank you for the invitation.
Thank you. So I'm going to read a little of your bio, and says that Roland Snooks directs the architectural practice studio Roland Snooks and is an associate professor at RMIT University. Roland's design research explores behavioral processes of formation that draw from the logic of swarm intelligence and the operation of multi-agent algorithms. Roland has taught widely in the US, including the Columbia University, University of Pennsylvania, SCI Arc, and the Pratt Institute. He received a PhD from RMIT and a Master in Advanced Architectural Design from Columbia University, where he studied on a Fulbright scholarship. In 2004, Roland co-founded the experimental architectural practice Kokuya with the intention of exploring the limits of algorithmic formation and its architectural potential. He directs the RMIT Architectural Tectonic Formation Lab, which develops computational design processes and robotic fabrication techniques throughout the design of experimental tectonics. Roland's work has been published and exhibited widely and acquired from the permanent collection of institutions, including the FRAC and Centre Pompidou. So really, thanks for coming, Roland, and start whenever you're ready.
Thank you very much for the invitation and for the introduction. I'm very pleased to be able to present to you guys today. So what I'm going to try and talk about today is 4 different parts of my practice, 4 different sort of research trajectories, and the way those things all tie together and the way they've operated through a series of different practice types or practice modes. So I'm going to talk about design process, and the design processes I'll be discussing are algorithmic or computational. And so they're looking primarily at multi-agent systems and the way agents interact to give rise to a generative architectural process. The second thing I will be looking at is form and aesthetics. And these things to us are very important, and we're very interested in the specificity of those, the specific nature of form and articulation. The third thing I'm going to discuss is advanced manufacturing, specifically around robotics and the way we're using robotics in order to build some of the more complex geometries we've been working on. And lastly, looking at tectonics. And what I'll be doing today is going through a whole series of projects that describe an evolution of tectonics. And when I'm talking about tectonics, what I'm talking about is a relationship between structure, surface, ornament, and their constructional logic, and where all these things are intertwined. So I've developed this work over a number of different modes of practice. The first of these, Kokuja, we founded in 2004, and this was with 2 partners, John Podborcek and Rob Stewart-Smith. And Kokuja was really set up to explore algorithmic processes and try to understand how could complex systems be applied to architecture, and what does that mean for aesthetics and for articulation. So this practice ran for about 10 years, and it was very much about doing highly speculative research. The second mode of practice that began in 2012 was when I moved from the US back to Australia and established a laboratory at RMIT University, which is now called the Tectonic Formation Lab. And this was really looking at the way we could use robots in order to build some of the complex geometries we've been working on. I guess at this point in our research, we realized that the things that we were designing weren't possible to build in the current construction paradigm. And so consequently, we needed another, we needed to sort of explore other ways of building. And so we've looked primarily at robots for that. And then lastly is Studio Roland Snooks, which is, I guess, in some ways a more traditional architecture practice. This is a practice which is trying to work through live projects and clients, and to try and take some of the innovations that have been developed at RMIT in the lab and previously with Kakuja, and take those innovations and try to find ways of realizing those in real buildings. And we end up collaborating with many architects as well. So to start with, I'll talk about process. Now, the processes that we work with algorithmically is an approach I describe as behavioral formation. And so behavioral formation draws from the logic of swarm intelligence and operates through multi-agent algorithms. And so this is a process in which we can, through writing computer code, we can encode our intention as a designer into a set of autonomous agents. And through the interaction of these agents, a type of self-organized intention arises and an emergent architecture. So in these processes, what we're looking at is the way a whole series of entities, we describe them as agents, interact. And in this animation, this diagram, you can see how it starts off as a cloud, as a random cloud of points. And through all their interactions, some type of higher form of order emerges through their relationship. So these agent-based systems have no understanding of the overall form they're trying to create. All they're trying to do is make a relationship or reaction to the agents that are immediately adjacent to it. And once all these interactions play out, and millions of interactions, then a higher order of complexity and form emerges from this process. Now, the algorithmic logic of this dates back to the work of Craig Reynolds. And Craig Reynolds was trying to simulate something he described as the Boyd's algorithm. This was an attempt to try and simulate natural phenomena. So flocking of birds, swarming of insects or social insect colonies, and trying to understand what were the underlying rules behind these systems and how do they form. I guess he was able to deduce that there's only really three fundamental rules behind swarming and flocking and schooling. And they're cohesion, so to stay close to the neighbors, to separate, to avoid collision, and to align, so to maintain a similar direction and speed to the neighbors. Now, in adopting this type of algorithm and trying to develop a way of designing through it, this was not an attempt on my behalf to try and make architecture swarm-like or flock-like or somehow biological. Instead, it's an attempt to try and take a whole series of intentions, my intentions as a designer, and try to rewrite them as a series of what we describe as behaviors. So a series of rules. And so instead of trying to think of your intention at the overall level of the project, we try to think of our intention at just the very micro scale. And how do all these micro scale intentions interact to give rise to something that's greater than the sum of its parts? So all of these behaviors can be described mathematically. They can all be described in terms of vector maths. And these behaviors are not something which are, one binary. They're not one or the other. What ends up happening is there's an interaction between all these different behaviors. And this is a way of thinking about design in a non-linear way. So instead of thinking about design as a sequence of a series of steps that you do or a series of priorities that you might have, this allows a whole series of different decisions or intentions that you have as a designer to all mix simultaneously and all negotiate between themselves as to the final result of the form, the structure, or ornament. Another key concern we have is around the substrate of agency. And so often when people are talking about multi-agent systems, they're thinking about flocks and swarms and things which are point-based. But it's very difficult to make architecture from clouds of points. And so we're interested in more hierarchical structures and how we encode agency into those. So we're interested in encoding them into the control points of a line so a strand, or into the vertices of a mesh, some type of network, or something I describe as an agent body. And this is a hierarchical structure. Basically, the body is an agent, which is made up of a series of strands. And each of the strands, the control points on those strands are also agents. I'll talk about that in more detail soon. And so the idea is that these agent bodies will swarm around and move around based on one set of rules, but then also connect to their neighbors. And these limbs will sort of reach out and make connections. Often we do this because we're interested in making continuous lines of structure or generating certain ornamental effects. So in this relatively subtle animation, you can start to see how all these limbs begin to subtly move in order to connect and make these continuous structural conditions. Now, this type of algorithm ends up generating a geometry which is not really surface or volume or lattice, but somewhere in between. It's sort of a thick, fibrous mass. And these are the types of geometries we're really interested in making and understanding how we can fabricate them and how we can make them architectural. Now, at a small scale, we can fabricate them directly. So this is an aluminium print. It's only about 600 millimeters across. It's relatively small, but it's incredibly intricate. This has 1.1 million agents in the model, and the member size is very small. So each of these members is about 0.4 of a millimeter, so less than half a millimeter in diameter. And so we're able to make this incredibly detailed and complex, intricate geometry. So this is a project we developed for the Pompidou Center for an exhibition called Code Le Monde about 2 years ago. And it has a whole series of different conditions. The edges are a frayed condition. There's more turbulent conditions under the wings of the project. And then you have different readings at different scales. As you start to zoom out, you take on very different reading as to when you zoomed in. So this is it in the exhibition at the Pompidou Center, and it's now become part of the permanent collection of the Pompidou. This project was part of a series of projects. Another related project is this RMIT ceremonial mace. So this is an object which is which is actually used in graduation ceremonies at the university. And we were asked to really try and embody the agenda or the ambitions of the university, which is really around innovative design and technology and the way those things would come together to make a symbol for the university. But one of the reasons why I wanted to show you this project was to talk about the relationship between things which are emergent and things which are top-down or directly modeled. So for example, the part of the mace, the shaft that's being held by the person here, by his hands, this has been directly modeled. And we're modeling it directly because we want a very specific type of section that somebody can hold. Whereas the top of the mace, the head of the mace, and also the foot of the mace, these are given much more freedom to emerge. And so in this, there's a gradient between things which are tightly controlled and directly modeled by us, and things which we set up the conditions for and allow them to emerge. And so this is a key thing about generative design. Generative design is often described as designing the design process, or set up the conditions from which something can emerge, as opposed to directly designing the object or the artifact. And so this is what we're interested in. You know, how do we have negotiation between those two things? How do we have some parts which are highly emergent, where we just set up the conditions, and other parts where we directly control? And in this image, you can start to see the transition from direct control to something more emergent. In some of our more experimental work, we're trying to take this to a logical extreme. And what we're trying to do is we're trying to basically hybridize self-organizing generative algorithms with things which are direct and painterly. And so we've been investigating a series of softwares which are really geometry painting softwares. And this is an idea where we can generate something algorithmically, we can bring it into the painting software, we can literally sort of brush the geometry digitally in a very painterly way. Then it starts to reform again algorithmically, and we go backwards and forwards through this process. And the reason we do this is we're interested in trying to create geometries and forms which are not indexable back to their processes. So you can't look at the form and say, okay, I understand that to be something which is computational, or I understand that to be something that's gestural. What we're interested in doing is trying to make something which is unique. It can't be traced back to its process. And so we've done a series of these explorations, and these are sort of abstract objects. And it's something we also work with our students. So this is an image of student work from RMIT University. And what we ask the students to do is to try and go through these processes, but really to try and develop their own sort of design sensibility or their own sensibility around aesthetics and form. And we use these as sort of proto-architectural things, ways of generating form, which we then start to, I guess they start to creep or find their way back into architectural projects. So in terms of form, we've, over now the last, I guess 18 or 19 years, I've been exploring the way you can use multi-agent algorithms to generate form and articulation and ornament. So in this type of project for the National Art Museum of China, we're interested in using these swarm algorithms as a formal generator to generate an envelope for the building, but then also generate the articulation, like all the small, in this case, glass scales of the building, and look at the way there's a relationship between between the form and its articulation. So instead of making something where those are created from different processes, we wanted to create them from the same process, so they have a sympathy between each other. They have a sort of reciprocal relationship, and then of course structure as well. So in this case, all three of those things are combined as a single logic. This is an older project that we developed with Tom Wiscombe, a well-known architect in Los Angeles. And in this project, we were really trying to hybridize between generative processes and top-down modeling processes. And this became something we described as a sort of strange feedback between the two, where we would model something and then we would generate, put it into an algorithm and generate something from it and then remodel it, et cetera, until we created a sort of sympathy between those things. And one of the results of that is something we describe as a polyscalar geometry. And this is a geometry in which the same type of geometry reoccurs at different scales and has different roles. So these types of strands in this project, on the one scale, they're used for form and for spatial organization. Another scale, they're structural. Another scale, they're ornamental. So what happens is there's a blurring between types of geometry and what the actual geometry does. And this is something that's increasingly important in our work. We've also looked at these strand-based geometries as ways of making exoskeletons for towers. We have a series of these studies where we were looking at how we could have a load-bearing external shell for a building, so we avoid the need for columns. And this was an attempt to try and take a single piece of geometry, in this case the shell, and have it negotiate between a whole series of different architectural roles or behaviors. And so in this case, this shell it's structural. It's also the facade and the skin of the building. At certain points, it swells up and becomes spatial and habitable. Perhaps if it went down to a final level of detail, you'd also describe it as being ornamental. And we're interested in this idea that you don't have a single piece of geometry that represents an architectural role. So there's not a column that takes vertical load, or a facade that becomes the skin of the building. But we're interested in how one piece of geometry can do all of those things potentially. We've also worked a lot on fibrous geometries and the way they're expressive, like this project in Kazakhstan, or this ornamental study for a ceiling in Warsaw. And in this type of project, we're interested in the way you start with a field of geometry, and from that field, some type of figure emerges from that. And through that process of emergence, a whole series of different characteristics emerge. So we have these sort of singular wing-like elements. At certain points, we have periodic repeating geometries. And as you zoom in, we see things such as this near symmetry. Now, none of these conditions are written as code. They're not part of the algorithm. These are all emergent outcomes from the interaction of the agents within the algorithm. And then look at the way these fibrous geometries might scale up to architectural or sort of infrastructure projects such as this bridge. Another concern we have is around mute forms. We're interested in forms that we import from elsewhere, in this case, taking these sort of geological or rock-like forms as a way of trying to undermine typical architectural articulation or formal languages. And so this is a project that we've recently built at RMIT University for a small meeting room that's made from fiber composites. So it's made from predominantly glass fiber. And we've also looked at this in the practice where we're looking at these types of mute forms and what the relationship between form and articulation is. So in this image, you can see how we're blurring between what is an actual formal move and then what is a move of coloration. So at a certain point as you move around this space, these colored patterns of the skins of these objects start to align and imply three-dimensional objects. And you sort of see how those three-dimensional objects carve in and sometimes Boolean from the objects and make these spaces, and sometimes just mark it and create coloration. And so look at this as a way of sculpting space. And in one of these, so this was a research lab we were developing at Monash University, and inside one of those pavilions is a sound recording studio. And in this sound recording studio, we milled custom foam for the sound attenuation in this. And this was using a reaction diffusion algorithm. So it was a way of generating that form and then milling that directly from acoustic foam. You can see some of the detail of that. So this relationship between mute forms, these sort of boulder-like forms, and the highly articulated skins is something we've been developing for a while. This is a project back from 2010, memorial and museum at Baba Yar, so a Holocaust memorial, where we're trying to make it, I guess, a dichotomy between those sort of very heavy exterior and then this sort of very intricate, intense interior space. And the way it sits on a landscape that's seen as a charged landscape rather than a neutral landscape. So if that's our interest in form, you can see a lot of the things we're developing really resist being fabricated from normative construction processes. It's not the type of thing you can take to a conventional construction company and ask them to build. And so we began to realize, as I was explaining, that we needed to find other ways of building. And so we established a robotics lab at RMIT University. And initially, we looked at a whole lot of different ways of using robots to build things and to fabricate. We looked at the way we could use robots to bend rods. We looked at using robots to form sheet material. So in this case, we're incrementally sheet forming titanium. So the robot's sort of pushing into metal to create a form without using a mold. A lot of our work has involved feedback. And so we are often using cameras and scanning and taking real-time information back to the robots, and they're responding to what they see. And so this allows us to respond to highly volatile materials. So in this case, the robots are spraying out expander foam. So it's a very sort of ugly and volatile material. But as it's doing it, it's scanning it, it's understanding what that material is doing and responding in real time. So it's a conceptual project where we're looking at this idea of, instead of designing something and then fabricating it, the design and fabrication happens at once. So it's all part of a real-time process, where you have an interaction between material and algorithm through the logic of real-time robotics. Early on in our robotics setup, we also did a lot of work with developing our own extruders, different custom extruders, and we've also looked at the way you extrude nutrients and respond in a slow robotics way to biological growth. So this is an example where a robot is basically tending to the growth of mycelium and reacting as it grows slowly. And some of our most recent work is looking at additive manufacturing, large-scale additive manufacturing, using a process called wire arc additive manufacturing. And this is basically, crudely, you could describe it as having a welding torch, a MIG welding torch on the end of a robot, which deposits down layer after layer of material. And so we've looked at using this as a way of developing these type of wireframes through almost like spot welding, as well as developing a layer by layer, more traditional 3D printing approach. So this is being printed, this is printed in steel. It's quite a rapid process. And then in this example, you can see in this printed cylinder, we've then come back and we've machined the outside of it. And that demonstrates the way this makes something which is entirely homogeneous. So it's a process in which you can either express the layer by layer, slightly rough articulation of it, or you can come back and machine it later and get a highly polished finish. And so this is something we've been working on in terms of testing some of the agent body geometries we've been working on and seeing how we could print those things directly in steel. But a lot of the work we've done over the last sort of 6 or 7 years now is really around large-scale 3D printing of plastics. And of course, you've all used, or many of you have used, small 3D printers to print perhaps architectural models, we're interested in the idea of perhaps we can scale this up and start to actually print parts of architectural buildings, parts of building components. And so this is our large-scale FDM 3D printing facility at RMIT. And about three and a half years ago now, we completed our first 3D printed part of a building that had to go through fire codes and building codes and get signed off by the government. And this is part of that research lab I was showing earlier. And it's 3D printed in polycarbonate. It's printed in 10 panels. And this is to enclose a small meeting room. And it was generated through an algorithmic process in which we take a surface, and each of the vertices of that surface is an agent. And as they start to interact with each other, they make these sort of wave-like or corrugation patterns. And you can see in this, there are two scales of corrugation. So a large corrugation, which is structural, and a smaller corrugation, which is really used for, I guess, micro stiffening, but more so for to create certain optical effects in terms of reflection and refraction of light. So you can see the panels being installed and the sort of zigzagged joints, chevron joints between them. And this is one of those panels being printed, workshop at RMIT. And so for us, this was an important moment in demonstrating that if we can get this through building codes and fire codes, even though it's a very small project, it proves the viability of actually printing architectural elements at a larger scale. That's the interior of the meeting room, and you can sort of see some of the light effects, some of the reflection and refraction of light. So that project led to a more recent project, which was similar in brief. We were asked to design a couple of studios that fit into a larger workshop and making space. And we're trying to create a relationship between those two studios where we have different levels of transparency between them. And so part of these studios are from solid material, part is glazing, and part is 3D printed translucent plastic. But what we were trying to do is create a relationship between them. So the same panel divisions in the solid material become mullions in the glazing, and then become reinforcing elements in the 3D printed panels. So this was originally designed to have carbon fiber reinforced ribs within it. So we could print with a relatively thin plastic and reinforce it with something which is structurally strong. And that those ribs then also form the joints between the various panels. Now, in the end, for various value management reasons and so the politics of the project, that was the carbon fiber was removed, and so we ended up printing it slightly thicker. But those ridges still remained as structural elements within the 3D printed panels. And so this was the first time when we didn't print one of the projects ourselves. What we actually did is looked at the way we could license our technology that we developed to a company in Australia who were then able to print this commercially for us. And this is an important step we see as a way of getting this work out of the research lab and actually into real building construction where architects can use these processes and these fabrication techniques. And as you can see here, there's a various different layering between these two spaces, and the way you look from one through another through these different levels of translucency. There's also been a series of unbuilt projects that looked at similar strategies, looked at these types of algorithms which fold and crumple the surface to give it structural strength, and look at this expressive capacity of this type of 3D printing. Okay, so that brings me to the fourth topic, and I guess the focus of this presentation, which is around tectonics. Now, as I said, I really define tectonics as the relationship between surface structure and ornament, and its relationship to modes of production or fabrication approaches, and modes of connectivity, the way parts connect to each other. And I guess this fascination in tectonics really came about with this image. This is an image we produced about 8 or 9 years ago. It was for a competition. And I guess after producing this, we were really, I guess this is the moment we realized this this image couldn't be built. I mean, image couldn't be built in conventional manufacturing processes. So we needed to find other ways of building it. And so I guess we embarked on a whole series of prototypes. Often these prototypes are gallery scale. They're things we put in exhibitions. And each one of them, we were trying to test a different way of producing that type of geometry, a different way of embedding structure and ornament and surface all into one cohesive element. So this is the first one we produced is this project we called Composite Swarm. And this is a fiberglass project with polyurethane core material, which is the agent bodies, the sort of the black patterning in it. And this was an attempt to compress surface structure and ornament into one irreducible assemblage. So it's similar to the first animation I showed. It starts off as a cloud of agent bodies, and through all the interactions, they generate a form, but also through the interaction of their legs and their limbs, they also create continuous lines of structure. And so this is an idea that the generation of form and its articulation and structure all come about through the one process. And then that structure is sandwiched between layers of fiberglass. This gives you a sort of detail of those agent bodies. And the way it was produced is we had 3 different body types, and these were cast in flexible polyurethane foam. And so those bodies could bend. They're very flexible, they're floppy, but they couldn't actually stretch. And so then we had to take that logic and build that back into the generative algorithm. So we knew that whatever was generated algorithmically could also be built. Doing this type of fabrication in fiberglass, when this is done in the boat industry, for example, it's typically built on mold. And so we milled a polystyrene mold, coated that in resin, and then had layers of fiberglass fabric. We then placed these flexible foam agent bodies into the grooves that had been milled into the surface of the mold, laid more fiberglass over the top of it, and then it gets vacuum bagged and infused resin. So basically draw resin in under vacuum, and this makes a very strong, very thin fiberglass surface and bonds everything together. And so in this case, the fiberglass it's less than a millimeter thick. It's 0.85 of a millimeter. So it's very thin, and it enables this structure, which is 2.5 meters tall, to be rigid. And so it's a strategy where we take 2 very flexible things, very, very thin fiberglass surface, and these floppy polyurethane foam bodies. But when those 2 bits of geometry, 2 materials come together, they create something that's very rigid, and they do that through geometry rather than material. And the way that works is that each of these agent bodies has a certain thickness to it. It's only about 1 centimeter, but that's more than 10 times as thick as the actual surface itself. And that structural depth creates something which is strong, creates a sort of sandwich panel. And also the corrugations it generates also gives the surface strength. And so you can see this is why it's important that we have these continuous connections between the bodies, because we want these continuous structural ribs to run through the surface. Now that was a very small project, only 2.5 meters tall. Shortly after doing that project, the same curator came to us and asked if we could do something which was 10 times the size. And so this is for an exhibition called The Future Is Here, and we're asked to make something which is a display device for the exhibition itself, but also this thing has to become part of the exhibit. It has to become a demonstration of what new technologies can mean for architectural form, space, and articulation. But in doing this, we had to develop very different ways of fabricating these types of composite fiberglass surfaces. So this is one of our last digital models before we started rationalizing the project. And one of the things we realized is that with the previous project, we could mill the mold for the entire project. It was only 7 square meters. But with this project, it was 10 times the size, 70 square meters. We couldn't mill that much mold. So we had to work out how could we use some type of reusable mold and rationalize the surface. So we started by doing a series of prototypes, trying to figure out what the local articulation of this, the way these agent bodies would fit at a couple of different scales. And then at a larger scale, trying to understand how we could economize on form in a certain way. So in the end, we made the project from 8 parts. 3 of them are flat, so they didn't require a mold, and the other 5 are curved, but they all come off the one mold. So this gray shape is a plan view of the mold that we used, and you can see that each of those panels has a different profile cut off that mold. So it allows a certain continuity of form. So each of these have obviously very similar surface form, but because they're cut in different ways, they sort of undermine the repetition of that. So you don't sort of see the visual repetition, but you get this sort of consistency of formal character. So to make a reusable mold, we couldn't use foam, so we looked at the way we could mill from MDF. And so we made a mold that was partly CNC produced. So this central part is about 1.5 meters across. But this becomes part of a much larger mold, which is made partly by hand by carpenters, and as you can see, partly by machine through milling. In a way, the mold itself is a small architectural project. It's sort of 5 meters by 6 meters by 3 meters tall. The articulation of this project has 2 scales of agent body inlay. So the large scale is made from milled foam and the small scale from extruded silicon. Now, because we weren't actually building this ourselves, we had a boat builder to make this, we knew that we couldn't just give them a whole series of flexible bodies and have them work out where they go. We actually needed to make the foam rigid so they could place these fairly large rigid pieces of foam onto the mold where we could have a drawing for it. And each of these bodies was responding to the structural analysis of the surface. So this is a bending moment diagram. So looking at the way the surface wants to bend. And these agents were programmed to be able to respond to that so they could resist those bending moments. And what they're trying to do is align their limbs in the direction of the bending moment force, and also to scale the size based on the relative load each of them have. Because we had to make all of these unique, we couldn't cast them like we were from a mold in the previous project. We needed to mill each of these bodies. So some of them were quite complex. Some of them which would involve double curvature meant we had to mill a jig, we had to mill the backside, then we had to mill the front side. So this was quite an involved process. And then once each of those milled parts were produced, they get laid down on a one-to-one template, a drawing that's on the mold, and then they are sandwiched between layers of fiberglass. So this is quite a difficult process, both in terms of the milling and fabrication of the parts, but also compositing it all together as fiberglass. So you can see here that those then get trimmed, and we designed the parts to be as large as we could fit onto the semi-trailer. And this is them getting installed at a gallery in Melbourne, at the Design Hub. And then later on we shipped this in, about a year later, we shipped it over to China for the Shanghai Biennale, where it was installed again. Now that was a very difficult project to fabricate. And so after doing that project, we realized that we needed to find simpler ways of building these types of geometries. And so we started to wonder whether or not we could build these geometries simply from flat sheet material. So this is an example where we are simply laser cutting metal sheet, and then by unrolling our three-dimensional geometry in a certain way, we can make flat sheets that when they get riveted together, force double curvature. So they force the form into being. So it means we don't need to have any drawings as to the way this gets produced three-dimensionally. We don't need a mold for it. We don't need to bend anything. Simply by riveting it together, it creates its own form. So after doing this in metal, we tried to go back to composites and work out, is there a composite version of this? And so this was a project we developed for the Tallinn Architecture Biennale in 2015. And instead of using steel, we were using the same process, but cutting out of sheets of carbon fiber and then gluing those sheets together, and then seeing how those sheets would then form this double curvature, which we would then sandwich between very, very thin layers of fiberglass. So in the end, this fiberglass is, in this case, only a quarter of a millimeter, so less than a millimeter thick, and the fiberglass takes all the shear force in this, whereas the black carbon fiber skeleton takes a lot of the primary forces in this. And so in this, you can see, again, this very tight relationship between structural logic and patterning or ornamental expression. Now, I guess the problem with that series of projects is it took our ambition, which was around these thick fibrous masses that I was showing with these metal prints at the beginning of the lecture, and those ended up becoming very, very thin, incredibly thin, incredibly surface-like. And so we realized we needed a different way of making these. We needed to try and work out a way that we could make something which did have that thick fibrous mass. And so we ran these sort of two parallel, I guess, investigations, one looking at surface and one looking at what we describe as lattice. So this is a project which is looking at metal rod bending. And so it's a process in which we have robots bend rods, but it was generated through a very volatile process. And it's a process in which whatever we were creating wasn't easy to go back and then rationalize it to ensure that it could be built. So we needed to take all the logic of building and put it into our design algorithm. And so what we did is we did a series of experiments with the way robots would bend metal rods. What is the distance between bends, maximum angles, etc. And then we programmed that back into our algorithm, knowing then that whatever the algorithm generated through this very volatile process, we knew would be inherently something that could be fabricated. So one of the things, though, we realized by doing that is we fabricated this in a very efficient fashion. We had 270 metal rods, about 1 meter long each, with typically about 5 or 6 bends in them. And the two robots could fabricate all of those in one day. But then it took 5 days and 5 people to assemble this and to weld it together. And we realized that it was really about the translation of information from the digital model to people who are assembling this. That was the real stumbling block. That was the thing that was slowing down the process. And I guess in a way, we realized we optimized the wrong thing. We ended up optimizing the fabrication where we probably should have optimized the assembly logic. Now, after doing that project, we looked at trying to scale that project up. So we effectively used larger rods, in this case aluminium, and larger robots, and developed a pavilion along the sort of similar lines, a similar logic at Tongji University in Shanghai as part of their Digital Futures initiative there. But I guess those two types of research we're doing, one around the thin surface and one around the lattice or the thick fibrous mass, they each had opposite problems. So the surface had no thickness and then the lattice had no surface. And so we realized we needed to bring those two things together. And so really this became a key project. This was developed about 5 or 6 years ago. It was a competition entry, which we didn't win, but we were trying to propose to bring those two tectonic logics together, but then also bring together our interest in intricate fibrous masses, as well as these sort of boulder-like geological forms, and how all these things could come together as one process. And so in the end, we had an agent body algorithm that was responding to a geological form that we had modeled. And so at one part, it's really sort of adhering to the surface of that. At other parts, it starts to unravel and make these more turbulent spaces and fibrous spaces on the interior. And so you see in the section that it maintains both of these conditions. It has a surface at one point, and it has a sort of thick three-dimensional fibrous lattice at another point. But we realized to be able to make this, we couldn't rely on the same techniques we had been, which was effectively trying to build the agent bodies in some way, and then to try and apply some type of surface. And instead, we realized that if we flipped that logic, maybe it would open up a whole lot of other possibilities. And so we thought, okay, instead of building the network and skinning it, what about if we built the skin and then cast the structural network into the skin? And so this is where we became interested in additive manufacturing and 3D printing. And so we developed a process in which we could print these thin skins with a series of conduits embedded into it, and then we could start to cast material back into them. And the idea was to be able to cast in this case, a fiber reinforced concrete lattice back into this, and that enabled us to have this very intricate, complex structure. And so we developed this through a series of prototypes. You can see here where we're casting concrete into those thin skins. This is something that was then tested through a series of series of projects, both sort of digital projects as well as prototypes. A year or two after doing that project, we were asked by the National Gallery of Victoria to try and scale up what we were doing into a large pavilion to go as part of their triennial exhibition. And so we developed this project, which is called Flow. And this is a collaboration with a sound artist called Philip Samantzis. And so you can see that the project is 3D printed out of plastic once again. And Philip Samantzis is a sound artist. He takes recordings from the Antarctic of melting ice and glaciers cracking and forming. And then what we were really tasked with doing is trying to work out a way of making a space which somehow embodied, I guess, the atmosphere of that. And so we tried to make something which was quite ice-like and I guess very atmospheric experience, which is a very different type of aesthetics and atmospheres, whether it was during the day or in the at nighttime. It has these very sort of different lighting effects, and whether it's illuminated from the interior or from the exterior, and the way that it starts to, as you look up through this, it frames the stained glass ceiling designed by Leonard French at the NGV. So this is sort of the major museum in Australia, the National Gallery, which is in Victoria. And so this project is developed through a swarm of 70 3D printed polymer panels. And so these panels were printed at RMIT, and each of the panels is, it takes about 4 hours to print these panels. And they're almost like a family of parametric panels. So each one is has a unique form, but they're all related in terms of their geometry. And each one also has a different level of translucency and glossiness. So some of them are high gloss and quite transparent, and then some are quite frosted. And we became quite interested in the lighting effects, the reflection and refraction of light through these panels. But I guess a key issue of this project was the relationship between skin and structure. So I've talked a lot today about how we were attempting to compress surface and structure and ornament into one continuous thing, and the way we were trying to skin these agent body networks, or we were trying to cast them back into 3D prints. Whereas in this project, we didn't have that opportunity, partly for a very pragmatic reason. We were given a very short period of time, only 3 months, from the start of design to the end of construction on this project. And so, because of the very short design time, the brilliant engineers we worked with, Bollinger Grumman, weren't able to engineer a plastic structure. They were only willing to engineer metal. So in the end, we had this slight separation between the metal structure and the plastic panels, which I guess is sort of against some of the ideological things we're trying to achieve. But in this project, it was a sort of a necessary, something that was necessary in the project. But what we tried to do is not make it simply a structure which we then clad with plastic, but we tried to intertwine the structure and the skin in a more complex way. So this is the unrolled agent body structure, and some of the engineering drawings from that. And this was made by CNC brake press folded steel plates, which were laser cut and then bolted together. And then all this project sits on top of a timber base. And the timber base is made from, I guess, what you describe as more conventional fabrication approaches, a combination of handcraft and 5-axis milling of the parts. The project also had a very tight time frame when it came to the assembly of the project. We only had 3.5 days to install this project on site, but as you can see, it's a total jigsaw of parts. We had over 300 unique pieces of metal. We had 70 unique plastic panels, all going together in a highly complex assembly. And so this is when we started to talk to our friends, Cam and Gwyl, and I believe that Gwyl will be talking to you guys later on this evening. They were just in the process of setting up their business Fologram, and we'd worked closely. I mean, Cam had worked for my practice for a number of years. He worked on a number of projects, and Gwyl and I had also collaborated previously on research. And so we asked whether we could trial what they were working on with the HoloLens as a way of assembling this project on site without any drawings, and whether we could use that as a way of speeding up the process. So basically, this is when we're assembling. This is what we're looking at. We're looking at a holographic model of the project in real space as we're assembling it. And there's a short video that the guys at Fologram put together, and this is showing the installation team. And you can see these guys are, they can see the digital model, and so with each part they pick up, they look at the digital model. It has a label for each part on the digital model. Then they go and get that part. It's labeled. They bring it in. They sort of rotate it until it fits the digital model, and then they bolt it together. And so this became a process in which we didn't need to constantly refer back to digital drawings like we did with the bent metal rods, and allowed us to assemble this project remarkably quickly, considering it as a quite experimental and complex project. So this is the assembly sequence. And you can see that the panels are going up with the bits of steel. So basically what we do is we assemble the steel and the plastic together, and then those things come up as a complete unit. And this was sort of finished just in time. You can see that the painters are just finishing as the opening happens, and I guess the audience comes through. This was a very popular exhibition. In the end, about 85,000 people visited this project in the first 10 days that it was open. So that put a lot of stress on the project. It meant that it's not a project that could be running late or over schedule. So I guess my criticism of that project is, as I was saying, the way that the structure and the skin were two different things, and we tried to align them as closely as possible, but they're still discrete and separate. And so since then, we've been working on ways of trying to get structure and skin to be more integrated. And so our first attempt was these studies. This was a project we were working on in Portugal that went on hold, and this was where we were trying to embed the steel within layers of 3D printed plastics. That also caused a whole series of problems. That's not a particularly easy thing to do. And then we went back to our previous work and said, well, maybe we could actually cast into it. Instead of casting concrete in, maybe we could cast carbon fiber. So this is where we start to tie it back to the carbon fiber, the composite projects we were doing a number of years ago. And so we started working with the aerospace company Boeing, and Boeing sponsors part of our research to look at this relationship between carbon fiber and 3D printing. And so what we're doing is printing a series of layers, so sort of structures inside skins, and then having conduits in there where we could embed carbon fiber. And so this was developed for a project which we exhibited a year ago at the Shenzhen Biennale in China. And so this is it's quite a sculptural project, obviously. But what we're trying to do is we're trying to bring together a whole series of different things we've been working on now, I guess, over the last 18 years. And I really feel like this is the one project which starts to successfully bring those together. And so we're looking at this relationship between things which are surface-like, but also deep structural lattices. We're looking at integration of skin and structure, integration of high-performance carbon fiber with 3D printing of polymers, which of course gives us the flexibility for all of this type of geometric freedom, and bringing all this sort of tectonic logics together, and of course through the algorithmic design processes into this one sort of cohesive element. So it's printed with 3 layers. It's not printed in simply horizontal layer by layer, but because of the complexity of the form, we've broken it down into a series of 13 parts, and each part is printed, some of them are printed with horizontal layers, others the layers start to curve around, and that allows us to create greater overhangs and to have the geometry start to sort of rotate through space. So this is back in our lab, printing one of those parts. And then once those parts are printed, it's sort of manually cleaned, and then we infuse the carbon fiber into the what we describe as a structural skeleton. And this becomes a combination of carbon fiber and cast polyurethane foam to give it structural rigidity. Then there's a whole lot of other details which are built into that, designed into that. So this is a series of steel plates that connect to it. This is one of the larger parts after it had the carbon fiber infused into it. Then these parts are being packaged up, crated up from where we fabricated them in Melbourne and sent to China, to Shanghai, to be installed. So I guess that's the last project that I wanted to share with you guys today. And I guess what I'm trying to do throughout this presentation was to try and explain the way we looked at these 4 different, I guess, research agendas, researching into algorithmic processes and multi-agent systems. And this is something we've now been working on for 18 years, looking at the types of complex forms that leads to, and then the way we could start to use robotics and additive manufacturing as ways of building these complex forms. But then most importantly, tectonics. And I guess the thing about each of those previous 3 elements, the algorithmic design, the formal studies, and the robotic fabrication, is that no one of those leads the rest of them. It becomes a negotiation between all of them. So although we started with a problem that we'd invented for ourselves through digital design, once we started to actually work out how to build things, we started to work out the limits of material, the limits of robotics, those things begin to inform what it is that we design. So I like to think this type of project here really becomes a hybridization of all those things, where it's not led by one thing or another, but it's really in the true spirit of complexity, which is about the negotiation of a whole series of disparate ideas, disparate elements, which negotiate together to create one cohesive whole. All right, so I'll end it there. Thank you very much for having me and for listening, and I hope we've got time for some questions or Q&A.
Yes, thank you very much, Roland, for this wonderful lecture. This has been amazing, and it's a pleasure to hear this for you. And yes, we have some questions. Remember, you can write your questions here in the chat, or just feel free to turn on your microphone and ask. And for those who are watching us from Facebook, you can write your questions on the chat and I can read it. So the first question is from Alejandro Forni that says that does mycelium get melted with plastic or fiber for print?
Can you repeat that question?
Yeah, sure. Does mycelium get melted with plastic or fiber for print?
Mycelium, okay. So what we do is when we're working with mycelium, in fact, this is a project that I haven't showed today, but it's a project we're working on and we're going to be exhibiting in March. We're working on a project where we 3D print from timber fibers, basically. We print a wall system and then we grow mycelium in that. And so what we're doing is we're growing mycelium, I guess, to really replace the foams. So in that most recent project we're obviously printing from a petrochemical plastic, and then we're using petrochemical foams in there and carbon fiber. We're also interested in the way we can move away from that and start to look at biodegradable materials. So we've been doing all this work where we're printing in timber plastic composites, growing mycelium into it. And so I guess it's not the mycelium is never melting because the mycelium is coming in at a later stage. So we sort of print the form and then use that as a sort of permanent formwork or sacrificial formwork to grow the mycelium into, and that mycelium operates, has some structural strength because it works as has some compressive strength. And I know that you had Philip Block talking with you earlier in the conference, and I'm not sure whether he showed his mycelium project, but he's also done this work with growing mycelium into molds and looking at its sort of, I guess, limited compressive structural capacity.
Okay, thank you. We have a question from Ronan Bolaños. You could open your microphone if you want.
Thank you. Great talk, Roland. I think the work you've been doing, it's very interesting. And yes, Philippe Bloch did show the mycelium early before. And have you been facing limitations throughout computer capacity whenever you work with the agent complexity? I mean, do you stop as far as your computer capacity give you, or is there another way to work it around? I don't know if my question is clear.
No, I think it's clear.
Okay.
This changes throughout time. I mean, we when I first started using multi-agent systems, this was back in 2002. And at the time, I mean, obviously computational power was significantly less. And so now, of course, most of the simulations we run, they run in real time. And so they only run for, perhaps a couple of minutes. But back when I first started doing this work and first started writing these algorithms, the simulations would take at least 3 hours to run something that was very simple. So I got to the point where, and this was when I was a student, so I got to a point where I just basically programmed my entire day around 3-hour cycles. So I would like send off a simulation, then go do something else, have lunch or whatever, send off another simulation, go to sleep for 3 hours, wake up, send off another simulation. And so you became the slave to the computer in a way, and the slave to its like cycle time. But of course, since then, partly we've worked out ways of writing much more efficient algorithms, and partly obviously it's an exponential increase in computational power. So we don't really suffer from that. But with some of the very complex geometries, like the first projects I was showing, which have millions of agents involved in them, we have to then look at ways of using parallel processing. And so we have to multi-thread the code that we're writing. We also look at using GPU. So we're actually doing a lot of our nearest neighbor calculations on the graphics card, which can do massive parallel processing much better than the CPU. So I guess we've become more and more sophisticated in writing code as a way of optimizing those things. So yes, to some extent, it has been a limitation, but I guess we're constantly trying to find ways around those limitations. And obviously, if something takes hours or days to compute, then it limits how many times you're going to iterate through that, and that really limits how quickly you can explore the possibilities of that design process. So yeah, we're always trying to create things that are faster. I guess the next computational hurdle we're coming to is we've been moving into machine learning and AI recently. And what we're doing is we're actually using machine learning to train our multi-agent algorithms. And so currently previously our multi-agent algorithms, we would write the rules for them. We'd watch what they do, and then we'd go back and change the rules and adjust them and try to get them to do things that we think are successful. That's not to say that we know what we want them to do before they do them. As they behave, we sort of learn from them. So in a way, like we're learning from what the agents are doing, but then we're trying to change the rules to try and fine-tune them. But instead of doing that process, we're now working on a process where we're trying to actually use machine learning and artificial intelligence to train the agents themselves. So they sort of they learn to be more successful. But this is a very difficult thing, because then that means you need to be able to very clearly describe what is successful. And so, when you do it yourself, you're making all these judgments around, why one form is better than another form, and ultimately one spatial organization is better than another one. Ultimately, these are subjective criteria. And this is, I guess, the really important thing about the way architects work. I mean, we play the subjective role in these design processes. And so even though we're starting to work with machine learning, I'm very cautious about trying to automate processes and remove the human designer from them. Now, obviously, we design the system and we design the inputs to the system, but I'm not really interested in making a system in which it just operates autonomously. I think it's actually the subjective decision-making, about the qualities and characteristics of something, which is really important for architects to be engaged in.
Yeah,
so
definitely.
And I guess the follow-up from are digital tools a limitation of what we do? I guess now it's actually becoming things like physical tools, like our robots. The limitations of the robot limit what it is we can and can't design. or the limitations of material. So we're finding that as we're printing, some printing processes, you're able to have, great overhangs and cantilevers. Others have to be more vertical, and those things start to actually affect the character of what you choose to design and model. So I think, thanks for the question. I think it's really, it is a really important kind of question, an important problem in what we do.
Thank you. Yeah, great.
Thank you, Roland. So we have the next question from Jair Vega. So Jair, you can open your microphone, please. Okay, or I can just read it. He says, hello, Roland. Congratulations on your work. It is out of this world, and the question I have are incredible. What are your design principles that you involve in each of your projects, and what kind of software do your team use to achieve those designs before digital manufacturing?
Okay, so I guess I'll start with the easy part of the question, which is around the software. So our multi-agent code, we've written all that code a library of code ourselves, and so we use that in different formats. I mean, originally we wrote that code in Java, and then we sort of rewrote it all in C#, and sometimes we make standalone applications from that code. So we just have something which just runs it without another piece of software. More recently, we tend to use this in Rhino, and so we actually run our C# code out of Grasshopper. So I guess Rhino and Grasshopper are increasingly becoming where we do control a lot of our geometry, but then we use other software for different particular problems or particular approaches. So for example, we often use Autodesk's Maya when we're trying to do subdivision modeling, although increasingly we're also doing that in Rhino, the latest version of Rhino. We use a program called ZBrush or ZBrush, and this is I guess a geometry sculpting program, and it's the program we've been using for a lot of those sort of painterly forms I was trying to describe, where we're going back and forth between gestural operations and self-organizing approaches. But in the end, the platforms don't matter to us that much, because most of what we do, we write the code independently, and it could operate in, it could operate in Rhino, it could operate in Maya, we could run that code in 3D Studio Max, or we could run it as a standalone thing. So mostly the code is not such a, the code's the important thing, the platform it runs in is not so important. I guess the other platform we are using more recently also is Unity, and that has some very good access to machine learning agent models in Unity that we can tap into, and we'd hybridize that with our library of code. Okay, the other part of that question is around design principles. Well, I guess my work has always been about an exploration of complexity and the complex sciences, and trying to understand how that can give us an insight into the way things come into being in the world. And so I guess what I'm trying to describe here is that the complex sciences demonstrate that all forms and structures and organizations that come about in the physical world come about through the interaction of small parts within complex systems, which lead to the emergence of higher levels of order and hierarchy. So whether this is a school of fish, or whether it's got to do with the way sand dunes are formed from the interaction of particles of sand, and we also see this in a whole lot of other virtual interactions, like the way stock markets operate or the way social networks operate. And I guess I'm interested in looking at all of that logic, and then trying to understand how can we make an architecture from that. So how can we take those types of processes of formation and start to think about the way we form buildings, and when I say form buildings, I'm really talking about designing buildings. And so I guess that's my primary concern. My primary concern is about looking at complexity theory as a way of thinking about the way we design and generate projects. And a lot of complexity theory, as I've alluded to in the talk, deals with the negotiation between different elements. And so, whereas modernism was really about reductivism in many ways. So it's about often about clearly articulating the difference between structure and services and skins of buildings, etc. And the fact that you would make exploded axonometric diagrams where you could separate out all the elements of a building as separate things. Complexity theory would lead you to do something which is different, which is about the integration of everything. Like, how can one piece of geometry do all those things? Or how can all the things that a building have to do be negotiated through one process and to make one cohesive whole, rather than something that's made from separate parts? And so I guess that's a sort of a really strong underlying part of my ideology. But in terms of where the actual individual projects come from, they come from a sustained body of research. It's not like when we get a project, we don't look at the project and go, okay, what's the site, what's the brief, and try and generate a project from that. What we're actually doing is each project is an opportunity to test and advance the research that we've been doing. And so you can see by showing that series of tectonic projects, the prototypes, I'm trying to demonstrate the way that each project leads to the next one. And of course, then they react to the individual site or the client's ambitions or budgets or programs or all these other things. Of course, they react to those things, but they're never the things that lead the projects. The projects are really led by a set of ideological interests and a set of methodological or process-based research that we've been doing. So sorry for the long-winded answer. I hope that addresses your question.
Yes, thank you. It was really clear. So we have another question here from Andres, who asked, which do you think is the next step in the digital fabrication?
Well, I think that it's clear that additive manufacturing is progressing really rapidly. So I was hesitant to look at 3D printing or additive manufacturing because my assumption was always that it was going to be too slow and therefore too expensive to work on a large scale. But I guess it was about 5 or 6 years ago where we started thinking about this idea of not trying to print whole parts of buildings, but print very thin elements and then use that to cast back other material. So to print a thin formwork and cast concrete, for example. And this allowed us to then only print small parts of the building, but bits that make a difference. The bit that allows you to have complex geometry or complex forms. So I think that, but in the last few years, we've seen additive manufacturing change dramatically. Things that weren't possible a few years ago are now sort of commonplace. It's amazing to see the progress of concrete printing in particular. Concrete printing has now just become like a service that you can just go and buy a concrete printer off the shelf. You can go and buy the cements and the mortars, especially designed for those things, or you can go to a bureau and you can just send a file and have something printed in concrete. This is not something that we even need to develop anymore as architects. This is now a mature technology. I guess what I'm interested in doing is looking at some of these technologies that are not quite as mature, like some of the metal printing we're working on or the plastic printing, and working out what the role of that might be in architecture. And I guess that's less about trying to invent the technology, but instead try to understand what its implications for design are. Like, how is architecture different if we 3D print it, as opposed to if we make it some other way? And to me, this is an important concern because often when a new technology arrives, we just use it to make the things we could previously make. And I'll give a few examples. One is, of course, around robotic bricklaying. You've probably seen this. Like, some of the early work in robotics is where researchers have used robots to lay bricks. And although technically it's quite challenging, and it's amazing that they've done that, it doesn't make a lot of sense in terms of the evolution of construction, because a brick is a certain size because a person can pick it up with one hand and pick up a trowel with another hand and apply the mortar and put it down. And it's the right weight that you can just do that all day. Whereas a robot can pick up 100 kilograms or 1,000 kilograms. It's not limited to this. So the idea of having a robot do what a human would do, to me, doesn't make sense. What makes sense is to say, what could a robot do that a human couldn't possibly do? You know, how can they make something that we couldn't possibly make another way? And to me, that's what's exciting. It's not about trying to automate what has been done before, but it's about saying, how does this open up a whole new way of thinking about design? But yeah, we see new technologies used traditionally. I often in my lectures give this example of the first iron bridge that was built in the 1770s, so you know, more than 200 years ago in England. And the bridge, it's built from metal, but it looks like a timber bridge. It's detailed like a timber bridge. You know, its structural logic is like a timber bridge, and it's because they knew how to build bridges in timber, and suddenly they had this, you know, material that was now more available or could be processed in certain ways, so they could build it from iron, metal. But they didn't. It took a long time to actually then change the tectonics or change the structures or figure out what it is that metal could do that timber couldn't do. And this happens we work with Boeing, the aerospace company. They make airplanes, of course. And it's interesting talking to them. They now build airplanes from carbon fiber, not aluminium. But they kind of have this joke, and they talk about carbon fiber, and they talk about it as being black aluminium. And what they mean by that is that they've basically brought carbon fiber in to replace aluminium on planes, but the planes haven't really changed. So there's a whole lot of things you can do with carbon fiber. It's kind of amazing, but they're not doing it. They're just basically saying, okay, we have this new material. It's a bit stronger. It's a bit lighter. But they're building it as though they're building it from sheet metal. And that will, of course, change. It will change over time, but it's slow. So I guess the future of, to come back to the question, I think the future is really around additive manufacturing. And I think that as architects, our role in this is to understand you know, how we can make buildings differently because of that technology. You know, how can we sort of rethink architecture because of this, and what possibilities does it open up?
Okay, thank you, Roland. We have another question from Monica Vasquez. You wanna turn on your microphone?
Thank you. I think a bit of the question has been answered in the previous one, but imagining the future, how do you see your studio in some years from now? Maybe working with some other biomaterials or some kind of projects, more social or something. How do you see yourself? Thank you.
Yeah, like, I guess my personal situation is I end up having, I'm between two modes of practice. I mean, I run a research lab at a university, and then I run an architectural practice. And so everything I'm doing is trying to negotiate between those two things. And the lab generates new methods and new processes and new technologies, and the practice really tries to implement them. I guess what I'm trying to do is try and build both those up and build them up in such a way that they have a sort of synergetic relationship between them. But in terms of what I see us doing in the future, I started to talk about some of the our shift away from fossil fuel-based materials. Like, we're interested in how can we get away from petrochemicals. I mean, a lot of things we're printing, they're plastics, and you know, these obviously have serious environmental implications that we need to, you know, we all need to address and think about seriously. We have a couple of different strategies for dealing with this. One is that we're starting to print with recycled plastics. Another is that we're investigating printing with recycled ocean plastics. Of course, we all know there's a lot of plastic waste in the ocean, and we're looking at the way printing with plastic could help to rectify that problem, could start to extract that material. As I was explaining before, we're also looking at biological material, like biodegradable materials, like can we print from sawdust effectively, or wood plastic composites, and can we, you know, use materials like mycelium to replace petrochemical foam. So there's certainly, you know, this growing awareness in my practice around around sustainability and the impact that our work potentially has once it starts to scale up. I guess another area that's important is around machine learning. I mean, machine learning is, more and more it's invading all aspects of our life and all technical fields. And I think trying to work out as architects how we use machine learning is an important question. And I think that, again, it's not simply about taking existing machine learning algorithms that are used for images or hybridization, but actually trying to figure out how we embed that logic deeply within our processes and the way that we work and the way and the types of generative work that, for example, that I do. So yeah, and I guess the other thing that's important for my practice is building these things. Most of the things I've shown you are small projects. They're either prototypes that exist in galleries, or they're small parts of other architectural projects. But I see no reason why these things can't be scaled up. I see no reason why we can't, print entire facades of buildings, or print metal structures of buildings. All these things are now entirely possible. What we actually need is people to believe in it. We need clients to believe in it. We need regulatory bodies to believe in it. And once that starts to happen, and the small projects are important for that. You demonstrate to people, you show them what can be done. But we need those people to come on board in order to be able to make these things sort of a large scale reality. And that's where we're clearly going. But that's, I guess, the real challenge that lies ahead.
Thank you.
Pleasure.
Thank you, Roland. I think there are no more questions. Somebody else have another question here?
I do.
Okay.
What kind of advice would you give to architectural students? Most of us are at school still, and we have a lot of troubles, or I mean, not trouble, but it's hard to try to design something out of the box. And I mean, just watching at your amazing work blows our minds. So we would probably are going to try to start designing crazy architecture, but we're going to have some discussion with our professors probably. So what kind of advice would you give us?
Okay, well, I started studying at a very conservative architecture school, and I thought I studied there for 3 years, and design studio was just a battle. I felt like I was always fighting with my professors, and I thought that was just the way architecture school was. And then I went to RMIT University after my 3rd year, and I realized that the more radical something I proposed, the more it was actually supported. And I realized that that actually, it's not always a battle. You just need to find the places that support what you do. I mean, if you're in a situation where you have to fight, you then just go and fight for things you believe in. But then, if you can get into a situation where you can study with and work with people who believe in the things that you believe in and have the ambitions that you have, then that can be very productive and important thing. So that's one thing I'd say. The other thing is, never believe people when they say that it can't be done. I feel like my entire career, I do things and people just say it's not possible. Like I design this algorithmic work and people say you can't build it. So then we work out a way of building it. Or people say you can't print plastic buildings. You can never get them through fire codes or building codes. But then we do that. So it's almost like every time somebody tells me something can't be done, I guess that's actually becomes the challenge that inspires me. It's like, well, no, we'll demonstrate it can be done. I think all things can be done. It just is how much dedication you're willing to go to. I mean, you need to pick the battles you want to fight, but you can kind of achieve anything that you want to achieve if you're willing to be persistent. And you can see in the work that I've done, this is 18 years worth of work. This is not something I didn't sit down one day and went, I'm going to invent agent body tectonics and print them with robots. It's something that sort of evolved over a very long period of time. And so I think we need to have a commitment which extends beyond any one project. You need to think about every project as being simply a step in the next projects. But yeah, I think probably the best advice I can possibly give students is to always take risk. Never believe people who tell you things can't be done, and always be careful of architects because they're the most conservative people. Architects like to think of ourselves as being, we're these kind of radical creative people, but actually as a profession, there's all these conservative cultural norms that are imposed upon what we do, which actually restrain what we do. So, I guess my advice is try and find a way to break free of that in whatever way is important to you. I mean, I've pursued a very particular thing that mattered to me that came about from the things that I was reading 20 years ago, and has sort of developed a whole kind of career of work now. But you need to find what it is that's important to you. Don't try and do what I do, or don't try and do what Philip Block does, or what you need to do is you need to try and figure out how to do the things that I can't possibly imagine. Do the things that I think are impossible. That's the kind of challenge that I think students need to aspire to do.
Awesome. Thank you so much.
So I think we have no more questions. So I think that's all for this Q&A session. And I want to say that I have no words to thank you for sharing this knowledge with us and for joining us in this adventure. We really appreciate that you accepted our invitation. And thanks once again, behalf the Atrica Committee, Linea Mexico, and all the people here today. And we really hope to see you again in another time.
Well, it was a pleasure coming to speak with you guys and engaging with the conversation and the questions. It's really fabulous what you guys are trying to do in Mexico. And I think, when students come together and try to reimagine what's possible, I think that, it's really limitless. And I think that, I would just suggest that you guys sort of keep pushing forward and good luck with the rest of the conference. And say hello to my good friend Will when you see him this evening.
For sure.
Okay, thank you. And you can join us in other lectures if you want to.
Thank you. All right. Thanks guys so much.
Thank you.